Hello, and welcome to the Chapter 1.3 Differential Equations lecture on modeling with differential equations. So first, this symbol here means is proportional to. More formally, a function f of x is proportional to g of x if f of x is equal to k times g of x for some proportionality constant k. So for example, if f is always double g, then they are proportional. And often, in modeling with differential equations, the only thing that we'll know a priori is that two quantities vary proportionally, and then we must solve for this proportionality constant using empirical data. So, for example, there are many models of population growth, but the most basic of these operates under the assumption that given unlimited resources, the rate of population growth is proportional to the population. For example, the more bacteria there are, the more mitosis occurs, and thus the faster the growth rate. And we can express this relationship as that the rate of growth of the population is proportional to the population itself. And this is equivalent to writing that dp dt is equal to k times p for some proportionality constant k. This section is on modeling with differential equations. It's about being given a situation and coming up with a differential equation to model it. And thinking of this proportionality is a good way of coming up with a differential equation. And the solution to this happens to be that the population as a function of time is c times e to the kt, where c will be the initial population and k is that proportionality constant. The bigger k is here, then the faster the growth rate, and that's reflected in that the exponent here will be higher. Here's another example, where T is the temperature of a body, such as a hot cup of coffee, in an environment where the ambient temperature is T naught. Newton's law of cooling states that the rate of change in the temperature of, say, the coffee cup is proportional to the difference between the temperature of the coffee cup and the ambient room temperature. And that makes sense. The hotter the coffee is, the faster it's cooling down, because there's a greater heat difference between the coffee and the room temperature, so heat can escape more quickly. Yep, so this says that the coffee cools down at a rate proportional to how high above room temperature the coffee is. And again, proportionality, that just means that this is equal to k times that. And we'll solve this equation later. But this is coming up with a differential equation for this situation. Here's another example. The spread of a pandemic disease. Let P be the population of a country and Y be the number of people infected. The disease spreads by spreading from an infected person to an uninfected person. And thus, it's reasonable to assume that the rate at which the disease spreads is proportional to both the number of infected people Y and the remaining number of uninfected people, which is the whole population minus the infected people. Think of this as the more infected people there are, the faster the disease spreads, and simultaneously, the more uninfected people there are, the faster the disease spreads, because there are more opportunities for it to jump to an uninfected person. So mathematically, this is saying that the rate of growth of the disease is proportional to both the number of infected people and the number of uninfected people. If either of them is larger, the disease has more opportunity to spread and thus a higher growth rate. And again, re-expressing this rigorously, that just means it's equal to the proportionality constant times the right-hand side. And we'll solve this equation later, and we'll find that it's a logistic curve, as we call it. So the solution to this equation looks like this. This should make sense. In the beginning, you have a patient 0, and the disease spreads slowly. There are not very many infected people. And as there are more and more infected people, then the disease spreads faster and faster. But then, as the population runs out of uninfected people, well, the disease can't spread to very many remaining people. There are fewer opportunities for it to jump. So the rate of growth slows down and approaches infecting the whole population. So all of these are differential equations that we'll solve. And in practice in the class, we'll do it in the context of being given some kind of word problem and then setting up the differential equation and solving it. This section is just about setting it up though. And here's a classic example, tank mixing. We'll be seeing this a number of times in the class. Suppose that a tank holds 300 gallons of water, initially fresh water. Brine water containing 2 pounds of salt per gallon is pumped in at a rate of 3 gallons per minute. Then the tank thoroughly mixes, and the mixed solution is pumped out at the same rate of 3 gallons a minute. Let A be the amount of salt in the tank after t minutes. Find a differential equation modeling how much salt is in the tank as a function of time. So think about this conceptually first. Initially, it's fresh water, and we have salt water coming in, mixing, and going out. So in the end, what should we expect the concentration of salt in the tank to approach? Well, it's 2 pounds of salt per gallon in the water coming in. So as that keeps happening and it mixes and goes out, then the tank water should be approaching that same concentration of salt. That doesn't happen instantaneously though. In the beginning, it still has some fresh water in it and the concentration will be lower. So what exactly is the amount of salt at a given time? This will be a differential equation because the rate of change in the amount of salt in the tank will vary as a function of the concentration of salt. The more salt is in the tank, then the faster salt is going out. So that's a relationship between the amount of salt and the rate of change in the amount of salt in the tank. Now, setting up this differential equation can be tricky, but I'll show you how to think about it. So the first thing that we need, well, there are A of t pounds of salt in the tank at a given time. And here we know that there are 2 pounds of salt per gallon coming in. So what we also need is how many pounds per gallon of salt is there in the tank itself, because that will be the concentration in the water going out. Well, the concentration of salt in the tank is the amount of salt in the tank per the number of gallons in the tank. And how many gallons are in the tank? 300 gallons. A pounds of salt per 300 gallons means that there are A of t over 300 pounds per gallon of salt in the water going out. So the first step is to get all the information about the in and out. Now, immediately trying to relate A of t to dA dt is not obvious at all. And the way to think about it is, what is the change in the amount of salt after, say, a microsecond? And a microsecond corresponds to dt, a little change in time. So the change in the amount of salt, which is dA, we will express in terms of dt. We'll have something and something. And then what we can do is just divide both sides by dt, and we'll have a relationship between dA dt and A. And again, we're doing this because thinking about the change in the amount of salt after a microsecond is much easier. Okay, so what is the change in the amount of salt in the tank after, say, a microsecond at a given time? Well, that will be the salt in minus the salt out. Okay, so a microsecond passes. How much salt is coming into the tank? Well, water is coming in at a rate of 3 gallons per minute. That water contains 2 pounds of salt per gallon. I highly recommend keeping the units because then we can do dimensional analysis. Gallon over gallons cancels out. And in total, we'll have 3 times 2 is 6 pounds per minute of salt coming in. Okay, 6 pounds per minute of salt coming in. And how many minutes have passed? Well, a microsecond, dt. So after dt minutes, minutes over minutes cancels out, and we just have pounds of salt in. Okay, so we found how much salt has entered the tank after a little change in time, and the change in the amount of salt is that salt entering minus the salt exiting. How much salt has exited the tank? Well, also 3 gallons per minute times, okay, how many pounds per gallon of salt is there in the tank exiting? Well, that's what we found here. A over 300 pounds per gallon of salt. The amount of salt in the tank over the number of gallons in the tank. And how much time it has passed? dt minutes. And once again, dimensional analysis. We have found that this is the number of pounds of salt that have entered the tank after dt minutes, a little microsecond. Okay, so now we have a relationship between dA and A, and we have our dt's here. We just divide both sides by dt, and we'll have our differential equation. First, let's simplify this. 3 times 2 times dt is 6 dt, minus 3 times A over 300 is A over 100 dt. Okay, divide both sides by dt, and we have dA dt is 6 minus A over 100. This is important. There will be problems in homework and maybe exams on a word problem just like this, where you will need to set up the differential equation. After all, computer algebra systems can largely solve differential equations for us now, but computers can't read or come up with a real-life problem that needs solving and make the differential equation from that real-life problem. Okay, but remember, this also had an initial value. This has a whole family of solutions. What is the initial value here? The initial value is the amount of salt in the tank originally. And it said that initially the water was fresh. So at time t equals 0, there are 0 pounds of salt in the tank. Now I would like to illustrate by having a computer algebra system solve this, and you can see what the solution looks like. Okay, so here's the differential equation that we found. I just replaced A with Y so we can understand it more easily. Y prime is 6 minus Y over 100 with initial value. Y of 0 is 0. The initial amount of salt was nothing. And enter. And this computer algebra system solved that differential equation. And yes, you definitely can use Wolfram Alpha to check your work on homework. However, don't just use it to do the homework, because remember that exams are proctored, and you certainly can't use this on exams. And regardless, it can't set up differential equations for you from word problems. So on homework, solve the differential equations yourself. You can use this to check your work if you want. Okay, now let's graph this, see if it makes sense. Okay, so that is the solution that it found. So at time t equals 0, there are no pounds of salt in the tank as fresh water. And then as it mixes, the pounds of salt in the tank increases, and it looks like it's increasing to an asymptote of 600. Does 600 pounds of salt in the tank asymptotically make sense? Well, remember that the brine water contained 2 pounds of salt per gallon, and the tank has 300 gallons of salt in it. So 2 pounds of salt per gallon times 300 gallons is 600. So indeed, it makes sense that it should be approaching 600 pounds of salt in the tank. So this checks out. And if we wanted to find the concentration of salt in the tank as a function of time, well, there are 300 gallons of water in the tank at all times. So we just divide the number of pounds of salt in the tank by 300 gallons to get pounds per gallon in the tank. And changing the window, we have this. So now it's pounds per gallon as a function of time. And you can see that it is approaching 2 pounds per gallon. Okay, cool, checks out. And practical application of this might be maybe water is contaminated in the city water, and they need to flush it out. So you can come up with a differential equation and then solve for at what time is the water 99.99% flushed out, and then you can be confident that the contaminants are at a safe level. That actually does conclude section 1.3. It's just an introduction to modeling. And the main lesson here was how to come up with a model from a word problem. So I know this is one of the more challenging topics so far, coming up with it, but study this until it makes sense and you feel like you could do it on your own. Have a great one.